Muy bien, ahí está. Esperamos un par de minutos a Moisés.
Sí.
Muy bien, pues vamos a iniciar, ¿no?
Oh.
No hay luces de Moisés. Okay, so let's start then. So first, let's give a review of last week's concepts. Justo, a interrumpir. Buenas noches, Moy. Ah, está ya. Muy bien. Okay, so I want to review some concepts of last week, but remember the goal is the same, to compute the cohomology, the ramp cohomology of some manifolds. We have computed the ramp cohomology for the real line, also for Euclidean space, and what else? Remember, so you are supposed to know the cohomology of which manifolds?
Hopefully Rn.
Rn, right? Euclidean space, that's correct. What else? We are missing an interesting one. Rn and what else? In the meantime.
Spheres.
Pardon?
Spheres.
Of any dimension?
No.
Which one?
Small spheres. One dimension.
Right, for the circle. So we have computed the rank cohomology of Euclidean space of any dimension and for the circle. Do you remember how did we compute the cohomology for Euclidean space? What was the main argument?
But it was contractible.
Yes, correct. And what about for the circle? Which argument did we use to compute the cohomology of the circle?
That one, it was this chain it was called.
Come again?
The exact chain, I don't remember the name.
Exact sequence. We use the Mayer-Viettori sequence to compute the cohomology of the circle. Very good. Okay, so let's start reviewing this. Remember that we use this concept of two manifolds having the same homotopy type because a consequence of this is that M and N will have the same cohomology. So that was like the motivation of this concept from topology. So we have two smooth manifolds. This is a review of the concepts of last week. And they don't need to have the same dimension. So we have two manifolds, and I have two smooth maps. Oh, sorry, this is wrong. This should be N, right? So I have two manifolds. They have the same homotopy type. If I have two smooth maps, such that the composite, it doesn't have to be equal to the identity, but has smooth maps, they have to be homotopic, right? And if we have these two things, we say that the two manifolds have the same homotopy type, right? And basically, this was the main observation of this concept. We care about manifolds having the same homotopy type because the induced map will give us a linear isomorphism. And also the other one, I only wrote F, but also G. G star is also a linear isomorphism. And we computed several examples of this. Here is a partial list. Remember, like the first one was like the motivation of this concept using the winding number. So the circle has the same homotopy type as R2 minus the origin. And also the n minus one dimensional sphere has the same homotopy type as the Euclidean space minus the origin. We show that Rn has the same homotopy type, has the space with a single point, right? And so using this observation, if we know the homotopy type of either one, we know, if we know the cohomology of either one, we know the cohomology of the other space. The cohomology of this is something trivial to compute by dimension reasons, and so we were able to know the cohomology of this, right? We don't know the cohomology of this and of this. We know that they will have the same cohomology, and this is one of the goals of this lecture, to compute the cohomology of the sphere. We computed the cohomology of the circle using the Mayer-Viettori sequence, and hence, you know the cohomology of the puncture plane. Now, another examples of spaces having the same homotopy type is the cylinder, right, and the circle. And if we look not only at S1 but or S2, if we have any sphere a neighborhood of the equator has the homotopy type of the equator. Okay? Now, the way that we prove this too, we actually wrote down the homotopy map. But we usually think, has this circle inside a cylinder, okay? And the homotopy map was like a picture, an animation shrinking everything to the equator. Okay, now some observation about this list of examples that we work it out explicitly. Spaces that you can have example of manifolds that have the same homotopy type, and the dimension doesn't have to match. Here, dimension 2, dimension 1, dimension n, dimension n minus 1, and so on. And the other thing about all of these examples is that they are very particular type of homotopy type. Because you see, this one is a subset of this one. Again, this one is a subset or a submanifold. This is a submanifold of this one. This is a submanifold. This is a submanifold. In general, for two spaces, you have the same homotopy type. One doesn't have to be a submanifold of the other. There's no need for that. But so this list of examples is something that we're going to show in a couple of minutes. They are spaces that have the same homotopy type, but they are a very particular class of examples. So the first one, so someone has been reading the book because or reviewing your notes from topology. We didn't discuss the concept of contractible. Salvador already mentioned that for Euclidean space. So a manifold is contractible if it has the homotopy type of a space with a single point. Okay? So that's what it means to be contractible. And the whole idea of a contractible space is that from the point of view of topology, it's very boring. There's no interesting topology on a contractible space. And this is what it is claiming. I mean, if something is contractible, it is the same as the space of a single point. And the space of a single point is boring. There's no topology there. And here is the list of examples. So this one, we already worked this one out, Euclidean space. But more generally, a convex space in Euclidean space is contractible. But because we are working with manifolds, that's why I put in here open. So in order for the set to be a manifold. So any open convex set in Euclidean space is contractible. And you can think of the homotopy. Being convex is that there is a point such that every other point, the segment lies in the set. Oh, sorry, I didn't want to say it is true for convex, but what I'm writing here, this is the star shape or star convex. So sorry for that. So okay. And the way that you can write down the homotopy is, again, you just parameterize each Euclidean segment. And in time, everything is shrinking because it is star convex. Okay? So that's a list of examples. For this one, we wrote down explicitly the homotopy last week. And for this one, you can work it out. Okay. Now, as I said before, the list of examples that we have shown that have the same homotopy type, they fit into this category here. So take a manifold N and consider as a manifold I. Then the whole idea is that the mixed set is going to shrink to the submanifold. And we will call that a deformation retraction. So the submanifold is a deformation retraction of the mixed manifold. If there is this homotopy map, remember that here this is not a smooth manifold because we have a boundary here. And what we did last time, remember that we replaced this by the open interval. And in that case, we have a manifold, okay? So keep that in mind. What is important is the concept of age. So what is a deformation retraction? So it will be a smooth function that satisfies these three conditions. At time zero, it is the identity map. Yes. At time one, I don't know if it's correct. Hold on there. At time one, yeah, so, right, no. Yes, no, I wrote S, this is correct. I got confused because I thought it was only on S, sorry. Remember, S is in P. Yes, so the second point means that everything has to lie in the small set at time one. That's all that I'm saying. And the third one is saying that at every point, S doesn't move. So here, S is in the small set, and P is the parameter. So S has a set, point-wise doesn't move, has time moves. Okay? This is for every P, S goes to S on the submanifold. So this is a deformation retraction. And the list of examples, we wrote down the homotopy, but all of these are examples of deformation retractions. Okay. For instance, I'm going to make a drawing showing this one, but it also applies to either one of them. Like, remember what was the map from this to this? It was the normalization map, right? So if you are already on the sphere, normalization is the same vector. It doesn't move. And we were moving along the ray. This point is not here. And what was the map that we used? We took any point and then looked at the unit in the same direction, and we parameterized this segment. And the homotopy was at time 0, I'm here. At time 1/3, I'm here. At time 1/2, and at time 1, I'm here. So if instead I start with this point will never move. If I start with this point, at time 0 is there, and it will move until time 1 is here. Do you remember what was the map?
X over its norm. Oh, P over its norm.
P over, this makes sense.
Time
P in non-zero, go ahead, times
1 minus T.
Okay.
Minus T times P.
Minus,
No, plus T times P.
minus or plus
Plus positive
T
times
whatever.
P.
But are you sure? I mean, because we need to normalize something, right? Or yeah, like this, sorry. Yes. So when P equals 0, let's move it around, right? I was saying it doesn't matter 0 or 1. Just keep in mind, I said T0 here, T1 here. This is the opposite, right? On P equals 1, you are here. On P equals 1. On P equals 2/3, you might be here. P equals 1/2. And with T equals 0, you are here. Okay? So either you replace this or between 0 and 1, it is the same aspect. Okay? And this is the general picture here. I have my whole manifold, S in my submanifold. If S is a deformation retraction, I have the map F. And what is going on? Somehow, if you are in a point outside S, you will be having a path, and the endpoint will be here. It will be a smooth collapsing kind of thing. The points already on the submanifold will never move. That's item 3 here. They never move between 0 and 1. Okay? So, without writing any equations, okay, this is S. And if I have points on S, they don't move. And the x-axis is a deformation retraction of the plane, and just think as a movie collapsing everything. You can go along the vertical line. This point at time 0 and at time 1 will be here. Any other point here again. So everything collapses, and there is no obstruction of doing that. So the x-axis is a deformation retraction of the plane. However, note that if I remove a point on the plane, say this one here, this argument doesn't work anymore. Okay? And it would not be true, actually. The x-axis is not a deformation retraction of the puncture plane. That would be false. Okay, and the way to argue that is that the cohomology of the x-axis, what is the cohomology of S? The x-axis. What is the cohomology of S?
Will be the same of a single point, right?
Right. And what is the cohomology of the puncture plane? Is it the same as the cohomology of R?
No, the same as the
Circle.
circle.
And what we will see now is that when S is a deformation retraction of M, both of them have the same cohomology. Okay, so no matter how hard you think about how to collapse everything on the puncture plane to the axis, it would not be possible. Great, so let's move on that then. This is exactly the next line of ideas. If S is a deformation retraction, then both bases have the same homotopy type. And again, this is something good for us because that means that they have the same cohomology. Okay? Good. So we have the map F that comes from the hypothesis, right? We know that F is smooth and satisfies the three conditions. So I'm going to call I the inclusion of the submanifold. And I'm going to call R this map. Okay? This map at time 1. Now, note the following. There's a minor thing that you need to consider. That map goes from M to M. Okay? However, the function that I want to consider goes from n to s. And because f is a deformation retraction, this map is well defined, right? Because we know that this belongs to s. So r goes from n to the small set is given by this. And also, you know that this happens. Right? Because f is a deformation retraction. Okay, so we want to show that these two manifolds have the same homotopy type. At this point, how can we show that two manifolds have the same homotopy type? Only by the definition. We don't have any other result that will help us to decide if two manifolds have the same homotopy type. We only have the definition, so we will proceed by the definition. And that's why we have this map and this map. I'm going to compose those two maps and show that they will be homotopy to the identity map. And in that way, S and M will have the same homotopy type. So we prove this by definition. I have the inclusion, and I define the map from M to S by using the homotopy. Okay, so let's compose now. Right? What can you say about the following map?
That is the identity already.
Identity where?
In S.
Right. And this is good. Now let's go the other way around. What is it? It will be I compose with R. So this will be a map from N to N. Right? Now, what can you say about this map? What is this map? So let's follow just the definition. So this is I applied to what? F of p comma 1. Okay? This point belongs to S, right? And this is equal to what? The inclusion is the point itself, right? Okay? Notice that here is exactly this one, right? Because this map indeed goes from M to N. It's not R, R goes from M to S. Okay, so is this clear for everyone?
Can you repeat that?
Yes, so remember the difference between these two. The only difference is the target. For this function is S, for this one is M. Right, so but it is basically the same map. or the same formula, so to say. But the difference is that for R, the target is S, and for F, the target is M. Although the image of this map lies in S, and not what we're using here. So this map, which is equal to this one, is a map from M to M. It's a map from M to M, and is equal to this one. So this map is precisely this one here. That's what I'm saying. That is, I'm saying that this map is precisely F at time 1. That's my conclusion here. Is that clear, Moises?
Yes, yeah, right.
Okay.
Thanks.
Now, but okay, we know what is the composition, but what I really want is for that map to be homotopy to the identity map on M, right? Because this is what we wanted to prove, after all. So I have one, and I get something stronger, equality. Here, I would like to have that this is homotopy to the identity map of M. And why is that true? Why can I justify this? Right? F, oh sorry, and here I put H. This map is a homotopy between F01, between F1 and F0. And in F0, I have the identity map on M. So F is a homotopy between time 0 and time 1. At time 0, I have the identity, and at time 1, some map. So this map is homotopy to the identity because F is a deformation retraction. So if a submanifold is a deformation retraction of the manifold M, both of them have the same homotopy type. Any questions? Okay, so basically we are done about the preliminaries to compute cohomology for the spheres and the torus and the other surfaces. We will use the Meyer-Vietore sequence That would be like the powerful tool. And this concept of spaces having the same homotopy type. So let's go and do some computations. Okay, so the main tool is the major vectoric sequence. And remember that that is a long exact sequence of vector spaces. And when you have a long sequence of vector spaces, the whole idea is to put, if you know that many of the spaces vanish, are zero, then things become much easier. So in other words, for a space to be zero means that the topology of the space is very simple. The simplest one is the contractible, right? So we will try to do things like that. So first, let's compute the Ramp cohomology of the sphere. We already computed the Ramp cohomology of S1. And remember, if we go more into the details, how do we compute the cohomology of S1? We choose like the upper hemisphere, lower hemisphere. We computed the non-exact sequence, the major vectoric non-exact sequence. And we were able to know exactly every vector space except one. The missing vector space was H1 of the circle. And because we had a non-exact sequence, we used a result from linear algebra. The alternating sum of the dimension has to be zero. And that's how we figure it out, that the dimension of H1 of the circle had to be 1. Because we knew all of the other spaces except for H1 of the circle. Well, now, here the argument is going to be a little bit different. But the philosophy is exactly the same. We need U and V to be open sets, and the union has to be the entire manifold. So I make U an open set that goes beyond the equator. So northern hemisphere and a little bit beyond. The same for V. It is the southern hemisphere, and I go a little bit above the equator. And so the intersection of the two, we can think of it as a cylinder. Although it is a little bit curved here, but it is basically an equator. A cylinder. Now, a question. Do you know the cohomology of these three spaces? None of this one, because that's what we would like to compute. So we don't know that one. But for those three spaces, do we know the cohomology of them?
Yes.
Okay, what can you say about U?
U is the cohomology of the disk, which is the homology of R2.
Right, so hold on. So U is homeomorphic to and open this in the plane, right? And then what else?
And that has the same cohomology as R2.
Something simpler. It is true. It is true what you said. It has the homomorphic type of R2, but also of
A point.
a point. And there's nothing different about the other hemisphere, so this is homeomorphic. To unopen this in R2, and you have the homomorphic type of a point. And what about the intersection?
It can be contracted to a circle.
So this has the homomorphic type of the circle. And we know the cohomology of the circle. Okay. Any questions? So we know the cohomology of the three spaces. And what I want you to notice here is in order to compute the cohomology of S2, I need to know the cohomology of S1, one dimension less. Okay, great. So now let's put all of this information in the Meyer-Vietori sequence. Okay, so U is a point. I have cohomology on degree 0. What about on degree 1? The cohomology of a point. Degree 1 and degree 2, the cohomology of a point. What is it?
0.
Right. And V is the same because it is a point. Right. Now, U intersection V, that's the cohomology of the circle. So now tell me what to enter here.
For H0 is R, for H1 is also R, and for H2 is 0.
Right. Okay. And then we start at 0. And this is the Meyer-Vietori sequence, goes all the way up. And it ends here because this is dimension 2. So I don't have a third row, a row in degree 3. So it ends here. Right? Now, we know this. What is this? We computed the cohomology in degree 0 for any manifold whatsoever. Even the most complicated example of a manifold that you can think of, we computed H0.
Was that R to the number of connected components?
Yes. So in this case, what is the answer?
Just R.
Yes, so this is R because S2 is connected. So we are missing this and this. Okay? Now, let's see. Yeah, let me unwind all of this, okay? So we have 0, R, and here, and then so if you unwind all of it, you only have this exact sequence. Okay? So in this diagram, I just wrote it down here. So what I said a minute ago, when you have 0, things become easy for us. Because, I mean, having this 0 here, this corresponds to this one here. So I can just split the exact sequence. I mean, I only care about this. The sequence is exact. 0 goes here. What do you know about this function? Because you have a 0 here.
That is injective.
Right, and you have a 0 here. So what do you have here? This map is injective because of the left-hand side. But if you use the right-hand side, what else can you conclude about this function? Injective and there's only one option.
Surjective.
Right? Having here this 0 map means that this is surjective. So, you see, because I have a 0 here, I can treat this long exact sequence has 2 small sequences. This one here and this one here. This here is very interesting because I have 0, non-zero, non-zero, 0. That means that this is a linear isomorphism. Injective and surjective. I have a bijective linear map, so this map is an isomorphism. This R, remember that it is this. Okay, so this has to be equal to R. And this map is an isomorphism. Okay? And now you have to go and analyze this. How do you compute the dimension of this?
It has to add to 0, no? Because we are going from positive, negative, so it has to be the same as R, some R, not 2R.
No. But I mean, that's what you have to do. The alternating sum has to be 0. Dimension 1, dimension 2, dimension 1, the dimension that you would like to know. So what is this? The dimension 1 minus 2 plus 1 minus this has to be equal to 0.
Zero.
Right? Because this is 1 minus 2 minus 1 plus 1, 0. 0 plus this one equals to 0. So this has to be 0. And now you have the cohomology of the two-dimensional sphere. In degrees 0 and 2 is R, and on the other degrees is trivial. Are there any questions?
Does that follow in general for any SN?
Oh, well, yes, we're going to do this next, but that's true. Yeah, this follows in general for any sphere. That is true. Okay, now, so I want to say something about all of this. So here is the whole non-exact sequence. If there is a 0 somewhere, the exact sequence splits. Okay? So that's why I will have only that exact sequence or that one there. Having a 0 is going to split my sequence. So that's one of them. And we argue this every time that this happens, this is an isomorphism. Or again, the alternating dimension argument. 1 minus this has to be 0. So this is one-dimensional. So a non-exact sequence is going to split. That's the other one. And because there's only one unknown, we use that argument about the sum of the alternating dimensions. Okay, so that's the first thing that I wanted to say. The second one, I'm not going to prove that, but if all of the spaces involved, so there are 4 spaces, the entire manifold, U, V, and the intersection, if those 3 spaces, 4 spaces, if those 4 spaces are connected like this, what you can do, you can actually start the major Victoria sequence in degree 1. You can just put here a 0 and start. When the manifold U, V, and the intersection are connected. So that is proved in the book. And because basically what you prove is that this map is surjective. So that means that this map has to be the zero map, and you start there. Okay? Any questions there? Let's argue that. This is connected. Then you have this exact sequence. Like this. I want you to think that this map is onto. This is what I want you to argue. Now, first of all, you need to remember what is this? What is the cohomology on degree 0? You already said, oh, has a vector space, this is Rn to the number of connected components. Yes, so that means this space is what? R.
Yes, R.
Yes, yes, but in general, so this means these are the locally constant functions on M in general. That's exactly the same as you mentioned before. Okay. Now, so here you have a function A, here you have a function B. Do you remember this map? I have a function on U, a function on V. What is the function of the intersection? So you restrict the functions, and it is the first one minus the second one, right? So again, it is a constant function. If this is the constant function A on U, the constant function V on V, then this map will give you the constant function A minus V here. Okay? So let's use this fact that this is connected. Take any constant. I have the constant function C on U, V. How can you assure me that this function is on the image? I need an element here that it will hit the constant function C on U intersection V. Give me an element here that maps here.
We can just guarantee the zero, right?
Again, please.
We can just be sure of the 0, 0.
So you can take the constant function C on U and the constant function 0. Right? So this function is onto. And if this function is onto, that means that this function, by exactness, is the 0 function. Because the kernel of this map is the image of this map. So the kernel of this map is this. So you can, instead of having this sequence, you can start with 0 and continue on. Okay? Good. So we can simplify the measure vectoric sequence in that case. And instead of starting in degree 0, we can start on degree 1, 0, and all of it. Okay, so that's a simplification that we can use. Right? Any questions? So let's make happy Moises with this. So let's compute the cohomology of the sphere. Good. Now, we will do this by induction. By induction on the dimension of the manifold. For n equals to 1, we computed the cohomology of the circle last week. And it was R in 0 and 1 and 0 on the rest, right? So let's assume that we know the cohomology of the n-1 sphere of all of the degrees, and let's compute the cohomology of Sn. Okay? So we must compute assuming that we know this. So what is U and what is V? And what is the intersection? So I want options. what u and v should we take?
Terms of the coordinate or just speak?
Again, please, Salvador.
And maybe we should consider again the hemispheres, the northern and
Right. So that's why I wrote this. So you can put something like this. So xn plus 1, let's say, sorry, open. Like this, right? So I'm going a little bit below the equator. So this is V. And then I have U, sorry, U. And I put a restriction here. And then I have U intersection V. So U comma V is an open cover of the sphere. They overlap on this set. You can actually write it down explicitly. Like this. Now, we want to compute the cohomology of this, and we need to come up with two open sets that cover the manifold. The whole idea is that for the other three spaces of both, we should know the cohomology of them. Because if we don't know the cohomology of this, it will be a very complicated problem to come up with the cohomology of the sphere. So we need to choose U and V in such a way that we know its cohomology. Now, what can you say about these three spaces in terms of the topology?
again U and V are like in this case Rn minus 1.
No. U is Rn minus 1?
No, like the Sn minus 1.
U?
Yeah.
They are contractible.
They are contractible, yes. What else? So U will be homeomorphic to an open ball, an n-dimensional open ball. Okay? So this is homeo to an open ball of dimension n. The radius is not important, some radius 1 if you want. Also, well, just like this. So, and now this one is contractible, so it is that. Okay? Now, I mean, a way to come up with this, if you want, you can take U, especially this U, to be the entire sphere minus the south pole. By stereographic projection, the whole sphere minus this point is homeomorphic to Rn. That makes sense, Salvador? Okay.
Yes, yes.
So the whole sphere minus this is homeomorphic to Rn by stereographic projection. So in particular, something like this, a hemisphere will correspond to some open ball in Rn. And in particular, now, the open ball, because it is a star shape, will have the same homotopy type as a point. Okay. The same is true for V, okay? Now, what about for the intersection? What can you say about that? We computed the homotopy type of that.
Yeah, it can be shrinked into the smaller sphere.
To the equator, which is Sn minus 1. So here is where we use the induction hypothesis. So we know the cohomology of this, we know the cohomology of this, and by hypothesis, we also know the cohomology of this. So let's fill this. U is homotopy type of a point. So tell me what to put here. So I want you to tell me what to put here, here, and here.
We're gonna have a lot of zeros in the middle, except for the first one.
Be more precise. So here, what?
R
R?
and R.
Okay. And then? Zeros, right? What about here? This is the n minus 1 sphere.
First one is gonna be R, and zeros all the way up to the last one, which is R.
R here or R here?
No, R in the yeah, that. And then 0.
Mm-hmm. Okay. So at least on these two columns, from here to here, everything is 0 except this one, right? So all of this is 0. And what I said before, In fact, we can omit this. And we can start the sequence here. Only zeros. And here zeros, right? So this vector space on this exact sequence is between two zeros. What can you say about this? I have a zero vector space, and here. What can you tell me about this vector space?
That it should be zero-dimensional as well.
In zero dimensional, right? Because what is it? So by this map means that this function is surjective. So it has to be the zero. Okay, now I forgot to put H2, but you see H2, again, it will be between a 0 and a 0, right? We will have the same picture. Except for N, right? For N, I have a 0 at the end, but not on the first one. But for this one, it's between a 0 and a 0. And the same for all of this. I have this. So you know that this do you agree with this one here? Up to n minus 1. I'm not saying n.
Yes, I agree.
I haven't reached this. But if you move along, you have all of them here. Remember that all of these are zeros. Everything here is 0. So that's why each of these vector spaces, unknown vector spaces, lies between a 0 and a 0. So except for degree n, I have this, but this is the same argument that we used before, right? What can you say about this map?
One is bijective.
It's an isomorphism. So there you have the cohomology of the sphere. I didn't write down 0 because it is connected, it's R, but on degree 1 up to degree 1 less than the dimension, the cohomology is trivial, and in the degree of the dimension, the cohomology is R because you get this short sequence of the major vectoric sequence. So the argument is more or less straightforward because we have many zeros here. This is the only non-zero vector space. That's the only one. From degree 1 and up. This is the only one. Everything is zero because this is non-zero. This is the same as this one. And all of this is trivial. And that's what we wanted to compute. The cohomology of the sphere is R in degree 0 and n, and it is 0 in the rest of the degrees. Any questions? Okay. Nothing? Great. So let's move on then. The next example, we will do it tomorrow. Let me just make you wonder a few things. Because I showed you how to simplify the longest subsequence in order to avoid this. Okay? But I want you to think about this. So tomorrow we will compute this. But in the meantime, what U and V do you think that they will be useful? I need a cover of the torus by 2 open sets. What is U and what is V? I need options.
That those cylinders.
Come again, Moises?
2 cylinders.
And in the intersection, what it would be?
2 circles.
2 smaller cylinders. So it would not be connected, right? So so we will have to work out either with the whole entire sequence, starting in degree 0, because U intersection V is not connected. And why did you thought about that?
Intuition. Like
No, it's on the cover. Come on.
really? Yeah, I would say. Yes.
Right there. So that's why. Now, that's one way. Any other options for U and V? Shame on both of you. I mean,
A bagel sandwich.
exactly. So you can cut it like this. And it's not a bagel, es una torta. Tortero. But again, the intersection will not be connected. Will be a cylinder like this and a smallest one. So that will be a different covering of the torus by two open sets, but the intersection will not be connected. U and V are connected, but not the intersection. Okay, so tomorrow we will work on that. And if we have time, I think we will. We will also compute the cohomology of the surface of genus 2. So those are the two examples that we will work out tomorrow. This one and this one. And basically that's the only thing that it is remaining for the curves. Compute the cohomology of this and of this. Okay, now once that we compute this, we will need something else to compute this. To compute this, we will use either of the two opening covers that you have proposed. But once that we compute this, let me tell you what is another covering. So I'm going to take U to be some open disk. And V to be the torus minus a point. This is open, this is open. You know the cohomology of this, right? That's contractible. Now, this covering is not used to compute the cohomology of this because we don't know the cohomology of the torus and we don't know this. However, if we know the cohomology of the torus, we will be able to compute now the cohomology of V. Because U intersection V is the homotopy type of what? V is the torus minus a point. U is a disk that contains the point. What is U intersection V?
The disk minus the point.
Right, exactly. So something like this. And what is the homotopy type of that? A circle. Right? Because this is basically the cylinder. You just put it flat on the table. So we will be able to compute the cohomology of the torus minus a point. And this will be useful for this because what is U? This is U. This is V. And the intersection will be a cylinder. So in order to compute the cohomology of this, we will use this U, which is a torus minus a small disk, like you're cutting here. V, a torus minus the disk, and the intersection is a cylinder. We know this is the homotopy type of the circle. We will compute the cohomology of this, and that will help us to compute the cohomology of this. Okay? So first we compute the cohomology of the torus, then we compute the cohomology of the torus minus a point, and then we can proceed for this one. So we will do that tomorrow. So the whole idea for tomorrow, the goal is to compute the cohomology of the surface of genus 1 and genus 2. And that's basically the only remaining topics that are left to cover. Right, so are there any questions? Okay, so then I will see you tomorrow. Okay, take care,
See ya.
guys. See you. A ver, 1, 2.